So you're welcome. Where are you joining us from?
From Oasis.
Okay. We'll soon start. Let's just wait for about 2 minutes for others to join. Can you see the screen? Can you see what I'm displaying on the screen?
Yes, I can see.
Okay, good. So today we'll be talking about the structure and composition of the atmosphere. So at the end of the facilitation class, you should be able to describe that the sorry for that break in transfer. I guess it was the network. So as I was saying, I said that at the end of this lesson, students should be able to describe vertical diminution of density with height, distinguish between isothermal atmosphere and adiabatic atmosphere. Explain the adiabatic atmosphere finite height and discuss the temperature profile of adiabatic process. I guess you have downloaded the course material. Have you?
Yes, sir.
Okay. So let's proceed. I said the atmosphere, this should be the atmosphere. The atmosphere is a layer or a set of layers of gas surrounding the planet or other material body that is held up in place by gravity of that body. Now, I said that an atmosphere is more likely to be retained if the gravity it is subjected to is high and the temperature of the atmosphere is low. I said the terrestrial atmosphere is characterized by the following properties. Please note those properties. I said temperature, pressure, density, composition, and motion. So you have 5 of them: temperature, pressure, density, composition, and motion. And the last statement there says that conventional meteorology deals with these quantities from the sea level to a height of about 20 kilometers. What that means is that when we want to cover meteorology of the atmosphere, we are talking about the height from sea level to a height, let's say about 20 kilometers above the ground. Now, having said that, we said that in the past, kites, balloons, and aircraft were used to assess this region, but in recent times now, there are other techniques that has improved the probing of the atmosphere, extended in height. Today, we can make use of rockets, we can make use of satellites to measure height at great altitude. So before, in the past, they make use of kite, balloon, and aircraft, but now you can use rockets and aircraft. Can you hear me? Are you still there?
Yes, I'm here, sir.
Okay, good. So I said you can make use of rockets and satellites now in real time. In fact, you can view the atmosphere in real time by the placement of satellites in the orbit. Now, we now say that Earth's atmosphere is a thin layer of gas held around the surface by gravity. So what is holding the atmosphere? Can you hear me? Hello? Sorry for that break in translation, it was network.
Okay.
So, Kauta has joined us. Hello, Kauta Adefunke.
Afternoon, sir.
Yeah. So, we started some few minutes ago, and we have just few minutes due to the Zoom app we are using. So we are discussing structure and composition of the atmosphere. And I said that the atmosphere is a layer of gases surrounding a planet or other material body that is held up in a place by the gravity of that body. So an atmosphere is more likely to be retained in the gravity it is subjected to. Is high and temperature of the above is low. So what we are saying is that an atmosphere is more likely to be retained if the gravity it is subjected to is high and the temperature of the atmosphere is low. So the gravity must have a higher temperature than the atmosphere. Now, we said the terrestrial atmosphere is characterized by the following properties. So we deal with its temperature, its pressure, density, composition, and motion. Now, we said conventional meteorology deals with these quantities from sea level to a height of about 20 kilometers. What that means is that you can study the atmosphere from a height of about from sea level to about a height of 20 kilometers. Now, having said that, we please have to take a small break. I'll be back with you in.
Okay, sir.
Sorry, I had to reduce the noise on my background. So
Okay, sir.
So we can proceed now. I said the terrestrial atmosphere is characterized by the following properties, which are the temperature, pressure, the density, composition, and motion. Now, I stopped here that I said conventional meteorology deals with these quantities from the sea level or from the ground level to a height of about 20 kilometers. And I've also said that in the past, kites, balloon, and aircraft were used to assess atmosphere, but in these days, we make use of rockets and satellites, and we can actually get the images in real time. What do we mean by real time? It means that we can get it at this instant. Now, we said Earth's atmosphere is a thin layer of gas held around the surface by gravity. And we said that 90% of the atmosphere's mass is within 15 kilometers of the Earth's surface. Please note all these points. It might come out in your TMA. Then we said that Earth radius is about 6,400 kilometers. We also say that the atmosphere is like a layer of paint on a basketball. I'm just trying to breathe out the point because this is not a normal conventional class, as we always say. We just give you points, and by the time, even under normal circumstances, you should have gone should have gone through the course material before coming to class, but I'm just giving you the point. I will also say that the atmosphere is a weak ionized plasma. Please note all these points. I'm saying it for the obtained time. And we also say that a neutral atmosphere is capable of executing wave motion of its own. Those are the things you need to know about the atmosphere. There's also another point that you need to note here, which says vertical diminution of density with height. What do we mean by diminution? Diminution means reduction. We mean vertical reduction of density with height. Now, we said the density of the atmosphere diminishes with height. This vertical diminution of density with height is one of the most striking features of the terrestrial atmosphere. Please note all this. The hydrostatic equation expresses the balance between the gravitational force at any point and the pressure gradient, the P, the Z. At that point, quantitatively, the hydrostatic equation may be written in form of the P, the Z to be what? Minus rho G. This is the P here is pressure, where rho is what? The density. And G is acceleration due to gravity. What they're just doing here is creating an expression to show that height, density of the atmosphere diminishes with height. So you start by saying the hydrostatic equation expresses the balance between gravitational force at any point, gives this, the P, this Z is the pressure gradient at any point of a gravitational, where a gravitational force is felt. And we said that the hydrostatic equation may be written in this form, that the pressure gradient is equal to the negative value of the density of the density and the acceleration due to gravity, and the height in question is Z. So moving on, we have it that, so we try to consider an ideal gas equation which says PV equals to nRT. If you remember your secondary school days, we can say that PV equals to nRT. So where P is pressure, V is volume, N is the number of molecules, T is the absolute temperature, and K is Stefan Boltzmann constant. We can, however, define the time temperature such that T equals to KT, which in form of we're talking in terms of energy now. That's why K here is introduced. Now, comparing this equation, this equation to what is up here, so we can say that anytime, anywhere you see KT, you can just write AT. That's what they're just trying to say. So that means that PV equals to NT, or when making our P the formula, it will now be N over VT, NT over V. Just like you're saying NKV, NKT over V. But we're saying that at absolute temperature, however, the temperature in energy units will be, the K will not be necessary. We're representing it with just T. We're just trying to make some assumptions there. So P here will now be what? N over T, representing N over V to be a capital N. So further mathematical illustration shows that the pressure P is distributed in accordance with this relation, P equals to P naught exponential minus integral of 1 over H dz. That's what this means, 1 over H dz. But this is how it is written mathematically. So note this equation here. This is what you need, because in your course material, they have broken this equation down. So further illustration of this equation give this. Exactly, they actually find the what's it called? The what they did was nt over n will give us, that's what we have this expression here, exponential equation here. But what you need is this one equation here, and for the pressure, the distribution of pressure with relative to height, then number of density is distributed according to this relation. So n equals to n naught t naught over t exponential dz d 1 over h dz. So note this relation and this. Now, what that means is that anytime we are asked to now, what is the illustration for density here? We said density it reduces it with height. Now, this is an illustration that says that hello, can you hear me?
Yes, sir. Yes, sir.
Good. I'm trying to break down this illustration to you that pressure, what is the relationship between density and height, or pressure and height? Now, pressure is distributed according to this, which is P naught exponential the integral of 1 over h dz. So this one shows that P is pressure is inversely proportional to the height. So as pressure increases, height reduces. So basically, you can also say that the number of the density n is distributed according to this as well. Now, this one is now showing what the relation we are actually talking about. Now, what they just did here was to how am I going to put it now? To replace this equation here with this P naught. P naught here, is that clear? Pressure times volume. What did you look at? What is it? What is here? PV here, or let's start from here. P here equals to NT. Then they substituted the P naught here. That's what they just brought into this place. And they now say that the density is inversely proportional to this height. So N here, which is the density, shows clearly that it's inversely proportional to height. So if you are told to show the relation inside your notes, but within the short time we have, we cannot break it down, and the medium of teaching as well. But these two relations must be noted. You have to write it down. There are some worked examples in your notes. I've gone through it over time, and it is valid. So this pressure decreases with height, so also density here, because they substituted the values here, which is this one is what's it called? A relation for density or mass over volume. This one can be said mass over volume, because N is the number of molecules which can be related to mass divided by volume. So this one gives us the density relation. So the density, so if you make N the summary formula here, it will be P over what? N will be what? P over T. That's why this T is doing here. Hello, can you hear me?
Yes, sir. Yes, sir.
Look at it from this angle. We said N equals to P over T. Now, but P is this. The whole of this. Hello? Hello?
We can hear you.
Yes, sir. Yes, sir.
Mathematical illustration shows us that pressure gives this. But here, we said P equals to N over V T. Because we said KT, it should be represented with T because it's in terms of energy. The constant is not really needed. Hello, are you saying something? Are you contributing to the class? Is there anybody saying anything? Now, looking at this, P here, the P here is this. Now, this P here is the P here. Now, what they just did was saying that N equals to P over T. So we brought this whole value of P into this equation. So divided by this T, that is why this T here is here. So the difference between this equation here and this one here is that we've made N the subject of formula here. This is number of molecules, which is referred to as the mass divided by the volume. Density is what? Mass over volume. So which is replaced by N. So making N into a formula, we now have this relation. So, but you must first of all refer to this, and this P is this P here. So bringing its value gave us this. Now, we cannot say that an isothermal atmosphere is one in which, hello, an isothermal atmosphere is one in which the temperature remains constant. These are just points that I lifted from your course material. Now, if you are told to now define an isothermal atmosphere, it's stating that it's an atmosphere in which the temperature remains constant. And this is an highly idealized case. In reality, the temperature of the atmosphere cannot be constant. Please let me tell you this. This particular illustration here will come out in your exam. Please note this. So if you have any questions as regards this equation, please speak up now. Hello? Hello?
There is no question, sir. It's explanatory, sir. You explained me very well, sir.
Okay, good. So this is necessary, and we just impute this value. So if you are told to show that height, vertical, the density of the atmosphere diminishes with height. So this is what you just give. You show this equation here, and you come back to this. So these are the things you show to actually indicate that density diminishes with height. Now, the isothermal atmosphere. An isothermal atmosphere is one in which the temperature remains constant. And we said this is not really possible in real life, in reality. And we said that to find a perfect isothermal atmosphere, it is not possible in reality. However, in the region of the upper atmosphere, the temperature profile shows very little variations with height. That means there's no change in temperature with height. So we can only get that one at a what's it called? At a height above us. So a possible explanation for this isothermality is the essence of a high thermal conductivity, which tends to smooth out any temperature gradients. And isothermal atmosphere can only be observed above a height of 300 kilometers. Can you see? We define isothermal atmosphere. We now say that in reality, it cannot exist except at a particular height. So the height is 300 kilometers, about 300 kilometers. So the atmosphere in this region tends to achieve thermal equilibrium so that eventually the temperature approaches a constant value. So I've been able to summarize at least the key points in that material. Now, let's go to the course material itself. Let's go to the course material itself. I'm trying to bring it up. In no time now, the Zoom will go off. Okay, let me bring up the course material itself so that we see what we have done so far, and you know that you have to read ahead of the class. Now let me bring it up. I'm trying to bring it up. Okay. Can you see it now? Can you see the course material?
Yes, sir. Yes, sir.
Okay. So
Yes, sir.
we've been able to deal with a lot. We've been able to deal with energy resources, environmental pollution. We've talked about that last week. So we just dealt with structure and composition of the atmosphere. I guess next week we'll be talking about artificial satellite and remote sensing. Let's see examples. Let's see some examples in the notes now, material now. I'm trying to scroll to where we are now. Okay, these are the things I summarized for you today. These are the equations. So if you go through these equations, you will be able to arrive at that final equation, which is this. It cannot be, which is this. So we just substitute that value into PNT, and you get your final answer. So you need to go through all that so that you have good knowledge of what I've been teaching. So the isothermal atmosphere as well, it has some equations in which you have to go through. So this is that if you go and you don't seem to understand, you need to now come back to class. We have talked about isothermal atmosphere. There's also adiabatic atmosphere. So you note that as well. You read that up. We said in the lower atmosphere, conventional motions are set up when the atmosphere is heated from below. So as a result, the gas which make up the atmosphere gradually below, so that the average mass remains practically unchanged with height. So note this. So you note these equations, these are the things you need to read up. It's only when you don't understand better, that's when you go to it together. We have a short time coming to class together and look at temperature profile of an adiabatic temperature. Those are the things you need to go through before the next class. So you go through that, you will read up the summary and also okay, can we go through these TMA questions together? Can you hear me?
Okay.
Yeah. So can we go through this together? In the following, answer true or false. The atmosphere of the Earth is strongly ionized plasma. Is it true or false?
Yes,
It's false. I said it in the material that it is a weak ionized plasma. Oh, okay, what I will do is that what you do is that you people should go through these questions. I think what I will do is go through these. How many questions? 1, 10, okay, 12, 11, 12, 13, 14, 15. Okay, you know what you will do? Answer those questions on page 31, on page 30 to 31, then send the answer, snap the answer and send it through the WhatsApp to me. Is that clear? Adoja Godwin, is that clear?
okay.
Okay, answer those questions and you get back to me next week. It's next week. Okay. So you can even send it personally to my WhatsApp. Don't send it generally to the individual. Should send directly to me. So by network is really cracking.
Yes, sir.
You should send it to me individually, and if there's any need for us to revisit it next week, we will. But I want you to go through all those things. The points that I've highlighted, they are points that you must note carefully. So next week, we'll be looking at Unit 3, which is artificial light and remote sensing. And I think that my time is almost up because of the nature of the Zoom we are using. Let me check. Let me check how many minutes I have. I still have enough time. So is there any question? Question, please. Hello? Question, please. Hello?
Hello, I can hear you, sir.
Is there any
I can
question?
hear you, sir.
I would like to entertain some questions.
God.
Hello? Is there any question?
Hello, sir. Can you hear me, sir?
I can hear you.
Yes, I have a question, sir.
Your line is not clear. Your line is not clear. You said what?
Can you hear me now? Yeah, based on the last minute.
Based on the last class?
Yes, sir. Yes, sir.
Okay.
I don't understand how tidal power plants generate energy. Can you just explain it?
I can't get that question. But probably what you do is that type it on, you're on the WhatsApp group, right?
Yes, sir.
Good. Please kindly, because I think your earpiece is not giving us a good audio. What you do is that type it on that WhatsApp group, then everybody will deliberate on it. Is that good by you?
Okay, sir. Okay, sir. No problem, sir.
All right. Okay, Victor Chukwuka, you want to ask question?
Yes, sir.
I can hear you better now. Please, can you please repeat the question? Maybe I should just answer you once and for all.
Okay, sir. The question is based on the last week because I go through it a bit. I didn't understand how tidal power plant is used to generate. Can you just explain a little bit on that?
Now, let's go back to that material. What we mentioned was that, I don't think we mentioned that tidal power, we are just, no, let's go to the objectives. We were trying to mention the sources of air, thermal, and chemical pollutions. Then, the tidal power plant is one of the 7 energy generating mechanisms. Is that clear? Hello?
Yes, sir.
So the tidal power plant,
yes, I can hear you, sir,
is one of the 7 what's it called? Energy generating mechanism. That was what I said. Did you get that? Did you get what I said?
Okay, but I get that, but I don't understand how it works, sir.
Now, the source, okay, 7, okay, let's go through the material again. 7 energy generating mechanism. Do you have your material there?
Yes, sir.
Good. So nuclear energy is one of them. It works by fission and fusion. Geothermal energy is energy from the ground. Then hydroelectric power, water. Now, we did not say that tidal power plant is generating pollution to the environment. In fact, it is stated here clearly that it has a minimal, what's it called? Adverse effect, because it works with wind. It turns, as the wind blows, there are instruments that has been, what's it called? Connected in such a way that it rolls the turbine and it generates energy. So that is what what's it called? That one is all about. In fact, it's written here that it's one of the 7 energy generating mechanisms. So the first one, so can you write down the 7 now? Can you
Yes,
write
sir.
that? So you can write the first one is the nuclear energy, the geothermal energy, hydroelectric power plants, tidal power plants, wind power plant, and the solar energy. Those are the 7 energy generating mechanisms. So the one before it are just the sources of air, thermal, and chemical pollution. Then thereafter, we discussed the adverse effect of energy resources on the environment, in which it can cause what we call a greenhouse. We can have a greenhouse. It can deplete the ozone layer. I think we mentioned that even before. I think it's mentioned here during the air pollution. So it can cause a greenhouse effect. It can deplete the what's it called? The ozone layer. So I think I've answered your question.
Yes, sir.
So Adoja, do you have any question as well? So it's just that the material is not properly arranged. So I think what you do is that go to page what's it called? Page 10 of your material. You look at the objectives. You should read with the objectives, the sources of air, thermal, and chemical pollution. Those are the ones you have listed. Then the 7 energy generating mechanisms, I've just read it out. Then the adverse effect of energy resources on the environment. We have talked about ozone layer depletion, then the greenhouse effect, and it also causes deforestation. Those are the 3. So I've been able to answer all those objectives, intended learning outcomes. So as well, what we talked about today, what we always do is that the high points, the highlight of the classes are always highlighted before each of the topic itself. So let me see. For this one we just finished now, we said that the objectives that describe the vertical diminution of density with height, which I mentioned this inside your notes, that height density diminishes with height. And they said you should distinguish between an isothermal atmosphere. In fact, assignment, distinguish between an isothermal atmosphere and an adiabatic atmosphere. Someone should type it on that group. It's a group discussion. Please, can you distinguish between a isothermal atmosphere? We said that isothermal atmosphere is not realistic, that it can only happen at a height of about 300 kilometers. What about adiabatic atmosphere? So explain adiabatic atmosphere finite height. So those are the questions you should look at and discuss temperature profile of an adiabatic atmosphere. So if you answer all these questions, I can guarantee you that if you don't score 80, it will be a mistake. So and I want you to have a high score. Those that took this course last session, I mean, the list of them got a B. And I want you to have the same as well. So I have less than 3 minutes, so it's better we call it a day here. We meet again same time next week. But Victor Chukwuka, you are on that group, right?
Yes, sir.
Okay, good. So please just drop those questions that I just mentioned, especially on the adiabatic atmosphere. I like the fact that you are following. I commend you. Any gray area you don't understand, bring it back to class, we clear it. But the thing is, you must read ahead of the class to make it more interesting. Is that clear?
Yes, sir.
So thank you for joining.
Thank you, sir.
So we call it a day here. Stop share. So thank you. So see you around next week.